All right. Okay, well, during the 5 minutes when we're waiting for the connector, pass the blue sheets, and maybe I can ask you to come forward more, because this room is very hard to hear in, and I want to make sure that, although we will try to be really close to the mics, that you can actually hear us and see our slides. So feel free to come further down. We do have a riveting program, so I know you're not going to want to escape out the back door. You have one. Yeah, that looks better. Yep, all right. Hooray. Hooray. Yay. The forces of research are victorious today. It's actually hard to have the mic close enough the way all the other things are cluttered on here, but I will try. So if you can't hear me, signal quickly, because I might not actually be able to keep the discipline to use the mic as close as it needs to be. The sound here is difficult. Okay, so welcome to the IETF 99's IRTF Open. We were told last night this is really IETF 99 and that we lost track of one, or we went one ahead. So there's a showing of the note well that's been adapted for the IRTF. Because we actually do follow, by consensus, we follow the IETF's IIPR policies. And this you've seen in all the other meetings, so it's not, there's nothing surprising here. In addition, I wanted to add, since we have the ability to add to process more readily than the IETF does, that we follow the anti-harassment policies. And this is just a pointer to them, since there wasn't actually a mention of that last night in the plenary either, that we have them and that there's an ombuds team if you have any concerns. I actually happen to also be one of the ombuds team, so if you have a concern about something in RGs, there's 2 other people on that team, so you can certainly consult Linda Cleaforth or Pete if you have a concern. And we're especially interested in just having everybody have a voice and speak up. It turns out we have one, so thank you so much. I apologize for your run. Somebody kindly ran for another connector. Okay, and next is that there is going to be a good bit of photography during this session because of the prizes. And if you have a concern to not be photographed, we have a policy that you can inform the photographer, please don't include me in a photograph. So that's one of the things that I wanted to also mention here. Okay, so that's all the policy. And I'm going to give a little bit more extended update because with the long panel and so on, I volunteered not to give an update during the plenary last night. In case you were wondering, it's not that we don't exist or that we were dissolute, it's that we actually tried to give some time back. We can have a little open mic session if you have some questions about the IRTF as well before we start the prizes. And then at the end, one of the discussion topics at the current IETF is the idea of having some sort of lightning talk session that would be like the kinds of lightning talks or they sometimes have other names that take place at research meetings. And it would be actually IETF and IRTF lightning talks mixed up together, possibly in an evening if we don't get bits and bytes back. So be thinking about that. You can always comment on that in the IETF discuss list, but we are interested in your opinion on that topic. I'll introduce the ANRP speakers when we get to them, but we have very good speakers. This is the last of the 2017 awardees this time. Okay, so in overview, as you know, because you're here, the IRTF focuses on the kinds of tasks that are not standards engineering, basically, but that seem important to the IETF and to the internet community to be tackled by people. We tend to work on applied research. We're not so likely to have a theoretical program here, although I suppose we could. We're organized into a parallel to the working groups called research groups, as you know. And there is an Internet Research Steering Group, which is all of the research group chairs and some at-large members, and I'll introduce them. But that's the basic picture of the IRTF. And it's been around as long as the IETF has been around, with different organizational relationships. Our current relationship is a close tie to the IAB, actually. So I thought people might be curious about some of the differences, because many of you go to RGs but may not have really thought about the way an RG is organized differently. The most important thing is that we have freedom to be very creative in how the work is done. So the goal is to have extremely impactful work, potentially work that will eventually solve a hard problem that we'd like a standard for, or solve a hard problem that standards folks need help with. But there's no requirement to have a strict process. So the groups can meet, they happen to meet at IETF quite a lot, but they can have meetings co-located with other organizations. They can have the lengths of meetings they need. We have in the past had closed research groups. We have none now. I would have to think really hard before we would charter a closed research group. But since all the research groups are open, the one caveat about meeting anywhere, wherever, is that they're held to the same process as the IETF of announcing where those meetings will be, with enough time for people to participate if they want to. Similarly, the output of working groups is RFCs, but the output of working groups research groups does not have to be RFCs. It could just be code. It could be a hackathon. It could be a series of publications in a journal. It could be an agenda that's used for another body, for a scholarly body. It could be a project of other sorts, and all of that is cool. So if you come to a research group meeting and they look like they're doing kind of IETF process, they don't have to be, and feel free to suggest, if you have a good idea for how to pursue their mission well, some other methods. We're very cool with experimenting, being creative. We want to get a great mix of people and a great mix of activity, and we don't need to be bound by publishing RFCs. And then definitively, research groups do not produce standards track documents. So that is one of the agreements that we have, that we are a parallel body that does not produce standards. Some groups aim to do their work well enough to solve some hard problems and then transition to creating a working group. Most recently, Disruption Tolerant Networking has done that. And this is certainly one of the modes that we like, but we would not be publishing standards track. We would be publishing informational, experimental, or open source, or whatever, up to the time that there's a transition to IETF. And then the other thing is that some groups do perform roles that are of service to the standards track. So one of the key examples of that is that the Cyphergy does crypto reviews that are sometimes extremely important and normatively required for documents in the IETF. And that is done with very close AD sponsorship. So that is another model. And if anyone has a question as we're going along, I'm also happy to answer questions. Okay, so it would be nice for people to get very involved. We're very open. We have a discuss list that's quiet and an announce list. The announce list is very quiet. You can subscribe to it and just get information about new groups and reviews of new charters and the prizes. The research mailing lists and all the wiki links can be found on irtf.org. And we are restructuring that page. You'll see some changes. My email officially, IRTF chair. IRSG is available. I didn't get enough time to put in the picture where the cats are not just looking at the TV, they're actually typing, because that's actually what we're looking for. But you can start out by reading the way they are. Those are my cats. They're at-large members of the IRSG in spirit. Oh, somebody meowed. This was where the picture of the typing cats will be later. So how do research groups originate? You may wonder about that too. And some of them have been around a long time, so their origins are lost in time, perhaps. I'm going to start requiring research group chairs to know who all were the chairs going back to the beginning, because some groups have really different feelings and structures now, but it would be good for them to actually have a sense of their past as well as their future. But the main thing about research groups is that they originate more freely than the IETF groups do. We are very interested in making sure we don't block something new that could be important that perhaps we don't appreciate well enough. By we, I mean me and the IRSG, but also you. So it turns out that you can propose a group, and with some tweaking to make sure that it has a sensible charter and that it has a mission and it has some, vision of what it should be doing, it can run for 3 meetings in a status of proposed research group before being considered for a more long-term gig. And we have 2 of those right now. So the way that we do the evaluation is they get to 3 meetings, and then the chair has a kind of review with the chairs of those groups to talk about how things have gone, but also we will start to have some more requests for a review by the community and by the IRSG there. So here's the set of research groups, and I'm happy to tell you that last meeting everybody met. This meeting everybody but the decentralized internet group met, and they met informally. They're actually not yet counting as having had one of their meetings, but we don't do that for too long. You can see what they are. They have a wide range of topics. I'm actually quite interested in soliciting a privacy research group, and if you have an interest in that, you should talk to me. We still have several of these groups still have to meet ahead of us, I don't have the schedule right in my head, but if any of the chairs would like to pitch their working group at the mic for the rest of the meeting, you certainly can do that. HRPC, Aubrey, would you like to come up and say a word? They're meeting Friday morning. Who else is still to meet? I apologize for not memorizing. Okay, so PAN-RG, maybe you'd like to mention PAN Proposed Research Group. Maybe you'd like to mention your plans as well. Is there one more still to meet?
Okay, this is totally embarrassing, but at the HRPC, I'll be giving an analysis of treatment of law, policy, and politics in the history of the RFCs, with a special emphasis on the first decade when there was a great deal of discussion about these issues.
And you want to say your name?
Sandra Brayman.
Yeah, so that should be a really great session. And Aubrey, you want to say a little more about HRPC?
I'm Aubrey Dory. I'm one of the co-chairs of the group that Sandra's going to speak at. So she already said the good stuff, but another thing though about the group is we just got one RFC out, and it's going to be time to sort of look at, okay, we've got some other things that are in the works, but how do we continue? So it's a great time to get involved in terms of how we continue.
Okay, good. Matt?
Yeah, Matt Ford. I just had a question about the DINRG. I was kind of looking forward to going to their meeting on Monday morning. It seems like it's been quite an active group while it's been meeting informally before. Can you say anything about why that meeting was cancelled? Because I think I heard something about the presenters were remote, but that doesn't seem like a strong reason to cancel a meeting.
So Melinda, do you want to say something about that? We have one of the chairs here.
Sure. Yeah, Melinda Shore, co-chair with Gert Kutcher. Yeah, we actually did have a problem with attendance by people who were doing active work. We're still sort of in startup mode, and we just were having problems getting enough active participation. So So yeah, we are going to be, we're talking about doing an interim in conjunction with NDSS, and of course we'll be meeting in London, but we thought it was a better idea to not meet rather than have a bad meeting.
Okay, and we have had very good meetings of the group so far, and I will put out a report with my observations about the groups on the discuss list. That's something that I need to get a better cadence for. Brian, you want to say something about the PAN proposed research group as well? Path-aware networking.
So we're going to have our second meeting of the Path-aware networking proposed research group right after lunch. Actually, I think we might be in here. I'm not sure. The 30-second elevator pitch is we're looking at it's kind of a fuzzy sort of architecture sort of thing. It's like what could we do in a world in which the endpoints have more active participation in the selection of the paths that their traffic takes. And this came out of an observation about a lot of sort of disconnected work that's happening in this space in the IETF, sort of things like IPv6 segment routing, things like PBDs, multipath transport protocols, work on these. How do all of these fit together, and what can we do with this stuff? So we're still trying to figure out, we're drawing a box around what it is we want to do, and we're still trying to figure out about interest in the room in this community. Is this correct as an IRTF research group? Are there other things that we should be doing in this space? We're doing a partial review of sort of the whole story early in the group, because we had an unfortunate conflict with the Ideas BOF in Prague our first time. So everyone's like, okay, for those of you who didn't come to the first meeting, here's what we're trying to do. And a few presentations where we're sort of diving deep on what we see as research into mechanisms for realizing path awareness end-to-end in the internet. So some of these are things that people know about, work that's been done in the IETF already, such as Alto, so getting path properties down to endpoints, and some of this is sort of bluer sky stuff. So please come by. That'll be the first afternoon slot. Thanks.
Thank you. Yes, do go by, do attend. So I want to also say something. Since we have a good number of research groups, I do participate in the scheduling rounds for the meeting. It's difficult to completely deconflict anything at the IETF these days, and we want to work on that. One thing that I hope to do is move this slot into a lunchtime so that we can make sure that, since we always have a lot of interest in the prize winner presentations, we actually have some ability to not conflict with people for that. And in general, I think we're just at the same mercy of time like everybody else. But the groups cover, span from I don't want to call other things out too much, but there's lots going on. We also have recently talked about having documents which are in two different groups, because network coding and ICNRG have interesting interaction between their work where they can support each other. So we may have parallel work going on that is really co-sponsored by two groups, and we don't need to have it owned by one group. We actually have the freedom to do that as well. So if you have any questions about other things, I'm happy to entertain them. Okay, you could see the membership. So the chairs are members of the IRSG. If you write to the IRSG mailing list, you'll get all these people. And then we have some at-large members as well who especially help to tie us back to, for example, the transport area. Spencer is one of our at-large because transport and IRSG have a lot of relationship. Okay, so people, we're going to have the two ANRP meetings, and I thought I'd make sure that we know as a group what presentations, what those are. Essentially, it's a best paper prize for all possible published papers in applied networking. And I like to say security too, because we have an interest in security, applied security topics, and you'll see we have had a number, lots. So they are for previously published papers. We're not very strict about the deadline, but it should be the last couple of years. And somebody or either nominates their own paper and themselves, or a paper and a speaker. And the speaker is specifically nominated in order to come and give a presentation. We select 6 awardees for the year at the beginning, before the year, but we announce them 2 at a time. And the prize winners receive some money, which has gone up for next year, and also a trip to speak here. And we actually have the resources to offer, if they request it, to come back for a follow-up if they've made lots of good ties and would like to follow up and spend more time at the IETF and IRTF. And the origin story is that Lars had a stroke of genius and created this, and it's a very good way for us to connect. I believe that's right, Aaron, it was Lars. And it's a very good way for us to connect between the larger research community and the IRTF and bring people that are not always here to talk with us. The Internet Society funds it primarily, but there are some sponsors as well. And you might be a sponsor if you think you could. It's not a large amount, but we certainly would love that. You can talk to ISAC about that. And thank you to Comcast for being a current sponsor, as well as thank you to ISAC. The process starts with a yearly call for papers. I hope you all saw it, because we tried to get it everywhere, and if we didn't, we need to do better. And it completed on November 5th. We actually got our largest number ever, almost 60 submissions, and very good ones to boot, which in my estimation, I'm not the only reviewer, obviously. We have a peer reviewing committee that is from academics and from industry, and you can check on the link there if you want to see more about the call for papers, the original call, who's on the program committee, things like that. And then before the end of the year, we will be, actually before the middle of December, we will be selecting all 6 and then start to announce the ones for 2018. So that is how that actually happens. That's where they come from. That's where Roland and Paul came from last year's group. So there's also the confusion because we have 2 A&R things, and people sometimes say, well, did you mean the W or the P? What is the difference between those? So it seemed reasonable to deconflict that for you today. They both have an annual call. ANRP calls for nominees. ANRW calls for papers. ANRW gives a prize for an already published paper. Piece. See, I'm doing it myself wrong. And ANRW gathers new papers, new submissions, or workshop submissions. The prize does 2 presentations at each ITF. The workshop does presentations at a workshop co-located with the summer ITF. We've chosen the program chairs for the ANRW. There's a steering committee for that, including Lars and Colin Perkins and myself and Sharon Goldberg, who many of you know, and Dave Choffness, who you may not know, are the co-chairs of the PC. And there will be more information soon about the rest of that. Okay, so hopefully you're no longer confused. And you might want to follow us at INRETAFO, which is our Twitter handle, and we also have a Facebook page. And you will notice that Roland is in this picture because he has been an awardee before, but it was a great sort of triumphant picture to attract people's attention, and I attribute to this picture the large increase in the submissions. So thank you to the people in that picture, and thank you to Olaf for taking such a good picture. Okay, so if there are any other questions, we're in a quick open mic for IRTF or RG questions.
Hi, Aaron Falk. So some of you may recognize me as the host of the Pechakucha, which is actually tonight. But I'm here because there's an idea under discussion to kind of take the lightning talk idea that has been, for Pechakucha, has been kind of a fun thing, and trying to actually make it available for people to present new ideas. So more of a serious lightning talk session. So I'm sort of at the center of a small group that's doing some brainstorming on this. So just to be clear, we're talking about doing a lightning talk session at the IETF sometime during the week. That's not going to conflict with working groups or research groups. If you have ideas or opinions as to whether you think that's a good idea or not, or if it's something that you've got some ideas on people who might be interested in participating, part of the goal of this is to do things like advertise barb-offs, advertise interesting research that's going on, but this is sort of like a 0 to 2 slide slot, so it's intended to be very fast, the kind of thing that they're doing in Dispatch, but to a broader, more general audience. So I would love to see researchers come and throw up a couple of slides on stuff that they think that they're doing, and so I think this is kind of a natural fit to the ANRP, ANRW discussion, and hopefully some stuff that will come out of this will lead to new research groups.
Thank you. Yeah, and so Aaron and Aaliyah are two of the key players there, and the IRSG will take an interest in this as well. So, definitely we're supporting this idea. We think it's a good one. Okay, so I'm going to introduce our first ANRP prize winner. Although I'll introduce you briefly because you introduce yourself in your slides as well. But Paul Emmerich is from the Technische Universität München in Germany, and he's going to present Mungen, which is a really interesting high-speed packet generator. And I will hand you the dongle now. Let's see, you need just this part of it, right? And you'll have to stand in the pink box. And yeah, great. It's working. Okay, great. Let's please welcome Paul.
Okay, yeah, thank you for the introduction. And yeah, I'm here to talk about my packet generator Mungen, and I'll just start with a rough introduction, who I am, where I come from, and then I'll go over a few aspects of Mungen. I won't bore you with any details about the implementation or performance evaluation or how we build it. I will instead just show a few key points and show an example about how you can use it, because in the end, this was about applied networking research, which often somehow includes a packet generator, and what I really want to show, how to use it and how it's different from what you might be used to when you are used to different packet generators, be them hardware or software. So me, I'm a PhD student at Technical University of Munich, and it said the German name on the slide before, because when we wrote that paper, we had the company policy that university-wide policy that we were not allowed to translate the name to English, which leads to these awkward moments, people trying to translate, to just pronounce that name. And we luckily changed that, I think, 2 years ago. And since then, I'm allowed to say Technical University of Munich, which is so much easier to pronounce for others. And well, I've been there since 2014. And I started as a PhD student, and I'm hopefully finishing soonish. I have to write a thesis and so on, and this is, yeah. I plan to finish next year sometime. I said it last year as well, but yeah. And my thesis will be about testing different network devices, where network devices can refer to a typical classical hardware black box. You send in packets out, it does something, you get packets back, but does it the right thing, how fast it is? This is kind of boring compared to a complex software system that can investigate a lot of different effects in depth, and where the performance is not always clear, where the bottlenecks are, and so on. And to do this, I kind of started this work on Mungen, or the idea, when I did my master's thesis, where I had a deeper look at performance of Open vSwitch and virtual switches in cloud environments. And I just realized there wasn't a really good software packet generator that you could just use and that did all the things I wanted to. And in the end, I always ended up modifying some code of some software packet generator to get it to do the things I wanted to. It was kind of annoying, and so I went with this idea of building a packet generator to start to really really be able to do what I wanted to do. I had to build this first, and now it seems to have consumed almost everything about the thesis, and it's mostly about the packet generator now. So where do I work at? What is the context that this work is being done in? This is the networking group at the informatics faculty at Technical University of Munich. We are a relatively large group of about 20 people, plus some external guys. And we do a broad range of network research topics. That ranges from everything from your usual traffic measurement and analysis, where we look at traffic, we have a mirror port at our internet uplink where we look for anomalies there. We do internet-wide scans. We do everything. We have our own autonomous system just for research stuff and for doing internet scans. Then we do, of course, all the hot buzzword things from software-defined networking and Internet of Things and the usual. We do a lot of security and privacy research as well, and peer-to-peer networks. And of course, the performance analysis and modeling part where I'm at. This is really the subgroup that I'm working in. And what are we doing there? It's, well, the main research question, or the main question that we have, is that packet processing becomes more and more complex. Networks become more and more complex. It's no longer just a few simple dumb boxes that switch around your packets. There are more software components in there. There is the important buzzwords from software-defined network to network function virtualization. And even when this is done in hardware, there's often a software component to it, and it's often even done in software nowadays instead of in hardware. Just last year, we had a project in the 5G area where we worked with a big company who were interested in doing some performance research of software components in the 5G backend, where a lot of stuff is being virtualized. There are virtualized network functions that need to be chained together. It's quite unclear how it impacts the performance if you have different things competing for the same resources. If you have different configurations that then run in software that can compete for hardware resources, from bandwidth to cache to memory to whatever. And so the research questions are from the sample saying, what are the important performance metrics? Sure, for performance metrics, you can just go to, let's say, RFC 2544, defines measure these things on your box, but it doesn't really work well for a software device compared to a hardware device. Clear, it's 20 years old and it was designed for hardware devices. There are, of course, new standard things, and the benchmarking methodology working group is also meeting today. That will be an interesting session. Then how do you measure things in a realistic scenario? What is even a realistic scenario? Do you just send some packets? What packets do you send? It's particularly interesting when you benchmark stuff like firewalls, where you might want to simulate some complex denial of service attack or anything. It can quickly get very, very complicated. And another big topic that we are working on is, how do you make a measurement reproducible? If you run this one thing once with your home-built packet generator on, and you are testing your own homebrew solution, this really, and how do you ensure that someone else can reproduce the results, or even that you yourself can reproduce the results in 1 year, because you might not have that server or that hardware any longer, or not that specific software version which might not run any longer because you upgraded your system. How do you keep that stuff manageable? And of course, how can you predict performance with models? How do you, if you are planning a network and you want to know how much hardware, how much software to buy, what hardware to buy, how can you do that? How can you kind of get a model for the behavior, for the performance, and kind of predict what you need to buy, what you need to plan, instead of just adjusting after the fact? So, and this is what I'm working with. We are lucky to have this big rack of test servers, which has a lot of 10 G ports and some 40 G ports. It's quite diverse hardware, from low-end power-saving 4-core CPUs to big NUMA nodes with 40 cores and so on, from small portable servers that we can drag somewhere to show off in a demo to these big boxes. And there are also SDN switch and an SDN router. And one key thing here that really makes work easier is that it's fully automated test workflow. That means if I want to run a network experiment and benchmark something, I really write a script that defines everything, that starts from, I want to use this and that server, I want to configure the switch that way, or I know that they're directly connected. And then there's a management node that allocates the servers exclusively for me. So I'm sure that only I'm using it and only my tests is currently running on it. And then this test script completely boots the server from scratch. This means there's no fixed installed operating system that might break and might challenge your reproducibility because you don't get the same system again. Instead, we do a PXE boot over network and just deploy the nodes as we need them, and we can get the same operating system again and again, and we can just reproduce the exact same software setup again and again, and it then collects some data and aggregates the data and already has some basic stuff, puts them in a Jupyter notebook, and so we can start running the analysis of the data on top of that. This is really nice, especially with the live boot. We have a big collection of operating systems and kernel versions. So if I want to run a test to see how different kernel versions evolved, and then I want to maybe afterwards, I think, oh, this might be another good metric, then I can just boot the old thing again and run the test on the old thing again instead of having to cope with downgrading an operating system or anything. So let's get to the main part of the talk. Really, this was just a longish introduction. This is about packet generators. So this is a big packet generator, which you might have seen or anything. There are a few problems with these big hardware boxes. First of all, they are big. Second, they are quite expensive. And as I've heard some nice guy from Intel explained it like this. So the problem with them shipping around extra boxes doesn't scale. This is, I think, true because often if you have multiple labs and you don't have a packet generator for each of them, then, or you might want some hardware features that are not available. In the end, people often go back to this fancy commodity hardware. Here are a few normal network cards. They are quite cheap comparatively. They are readily available. You can just plug them in your server and use them. But then you run into a lot of problems because, of course, there's a reason why these big hardware generators are so expensive, and they are very reliable and precise at what they do. Whereas if you use a software packet generator, it's typically, it might be slow, it might be imprecise, it might be unreliable, it might just give a different result every time you run it. And this is the problem that I'm really trying to solve here. I'm trying to combine the advantages of both software and software and hardware packet generators. That is, software typically cheap and flexible, and hardware typically very precise and accurate. And so the 5 main design goals that I had when building this, first of all, it had to be fast, obviously. So this is building on top of the DPDK framework, which is nowadays a Linux Foundation project, which is just a set or collection of drivers, optimized drivers, kernel bypass drivers for network cards, and some utility stuff for whatever you typically need when building a network app. And then on top of this, I built a nice-ish API to build packet generators, and everything I built about this was always explicitly with multi-core and multi-threading in mind. If you will show a few examples of how a typical Moongen script looks like, it's always, at its core, it's always explicit multi-threading and explicit multi-core, because that is really the only way to scale to higher speeds. Sure, a single 10G link, you can fill that up with minimum sized packets, meaning around 50 million packets per second with a single CPU core. That's not too hard as long as you're not doing too complicated things. But as soon as you go beyond that, you need to be able to run multiple threads at the same time. Luckily, modern network cards make this really easy because they offer this multi-queue interface, and they are natively doing a multi-threaded approach in hardware. So the software on top of it really fits quite nicely with the hardware. Then I wanted it to be flexible because from my experience when I used packet generators, I always ended up modifying the code at some place and doing something because I wanted this weird protocol and then it didn't support this weird protocol. Or just one simple example, I had this requirement. I wanted to generate different flows only at the layer 2 level, meaning I wanted to modify just the MAC addresses, and the packet generator we were using at the time didn't support it. So I went the source code and changed it and patched it and so on. And the change then I did was, okay, I had to modify the source code of 4 packet generators now. So this doesn't, all these configuration languages, they didn't seem to scale really. So what I did was for Moongen, I give full control of the main application to the user, meaning that if you use Moongen, the core idea is really that you write the code for the main transmit loop yourself, meaning every single packet you send out goes through your code and gets executed in real time for that packet. And for that, we are using the scripting language Lua, which is, has a very, very nice just-in-time compiler that allows us to really run custom script code for each and every single packet, because it really integrates very well with lower level things, and you can get direct access to the packet memory without pesky things like bound checks or anything, but just be careful when you write your test. Then another thing that was traditionally very, very challenging for software packet generators is timestamping, meaning that you want to maybe people often only evaluate if you read some academic papers about their great new whatever router or whatever switch, they often only give you, okay, this is the number in throughput, it manages this million packets per second, or even worse, this bandwidth, which is typically the software devices are restricted by packets per second and not by bandwidth. But you rarely see latency because it was just so hard to measure with a software packet generator. And especially in academia, people rarely have these big, expensive hardware boxes. So I really wanted to change that. And of course, turns out timestamping, doing it precisely in software is a challenging problem. But if you read the data sheets of your typical commodity NICs carefully, you can find some tricks how you can convince the hardware to timestamp packets. Basically, the hardware often has support for the PTP time synchronization protocol, which needs to support hardware timestamping in order to work properly. And if you then craft packets and trick the hardware a little bit, patch the driver a little bit, then you can get the hardware to timestamp almost arbitrarily packets. And this gets really nice results and really nice insights into software or hardware boxes that just weren't possible with software timestamping. Another thing that is quite an interesting thing and was more important than I initially thought was doing rate control, meaning controlling the traffic pattern that is sent. That is the gap between packets. Like if you want to send 1 million packets per second, I can send 1,000 packets, sleep for some time, for like a millisecond, send another 1,000 packets, sleep for 1 more millisecond, and then you get at 1 million packets per second. But I can also sleep between each packet for 1 microsecond, or I can do a fancy Poisson process or any more complex pattern. And this turned out to be hugely important when investigating software systems, and an aspect that's unfortunately often ignored. And then, of course, I wanted to make it open source, because what's the point if only I'm using it? I wanted to make it really easy to use and freely available, so you can check it out on GitHub. And what I'm now going to show you is just the only a few measurements and a few results, basically. And I don't want to bore you with the details. You can go to the paper, which is the citation is down there, if you want the gory implementation details. But I really want to show some examples of how to use it, how the usage is, and why a few things are important. And this is the traffic patterns. This is really a point that I really like, because it was just so much more important than I initially thought, and it's so often just ignored. People just send a burst of packets and say, oh, the average rate is fine, let's call it a day. Okay, so this is kind of big, confusing graph, but it's actually really easy. This is a really simple test setup. What I did here was I took 2 servers, connected them with 2 10G links, and run Moongen on one of them, and different packet generators, but that's a different paper, and Open vSwitch on the other one, and just forward packets with Open vSwitch. No fancy packet modification, nothing. No fancy Open vSwitch configuration. Just take packets from one port and send them out on the other using the normal Open vSwitch kernel module. You think, okay, this is a really boring test. But if you dig down into even such a simple software forwarding case, it really shows you what kind of complexity is hidden behind this seemingly simple example. So this graph shows the x-axis is the offered load, meaning I'm increasing load. In this case, it was restricted to 1 flow. The forwarding device was restricted to 1 CPU core, because if you go multi-cores, NUMA, then this opens a whole new can. So the simplest possible thing, and I configured Moongen to use different burst sizes. The default, I just generated constant bitrate traffic, meaning a constant gap between the packets. And this is the baseline of this measurement, meaning 100%, and the measured thing here is the latency relative to that case. So what you would expect if you run your packet generators a few times on the same case, you would expect the device under test to show the same latency response, because why would it be different? And especially you would expect to get the same latency result if using different packet generators if you don't change your device under test. But what we did in the past, we had different packet generators and got completely different results for the latency of the same device under test, so we investigated this further. And this graph is what I'm varying here with the different graphs in that diagram here is just the burst size, meaning the baseline, 1 packet, sleep for some time, 1 packet, and so on. And then 4 packets, 16 packets, 32 packets, and so on, and see how the latency relatively to the base case changes. And as you can see, even with something as a burst size of 4 or 16, you can quickly get a relative latency that differs by 100% or so. So you just get a completely different result just by changing how the packets are spaced on the wire without even going into anything from the contents of the packets, just changing this one thing. And the problem is why I'm showing this is that people often send burst as the default case, because it turns out software packet generators are only really fast if you have a naive implementation, if you send out bursts, because all these frameworks are always optimized to do burst packet processing or batching or vector or whatever you want to call it. All of it is optimized for this. And so the typical default burst sizes are between 16 and 256 for software packet generators. As you can see here, this is a really bad idea if you do latency or if you want latency measurements. It doesn't matter so much for the maximum achievable throughput that was around 2 million packets for all these configurations. And now it was really tricky to get different packet generators. We have another paper on this where we compared a lot of different software packet generators on how reliable they can generate what we configured them to do. At first, it turned out to be very hard to even get them to even try to send CBR traffic. Some claim to send CBR traffic, but then have some optimizing. Oh, sorry.
Do we need a different mic?
Here.
Thanks. Thank you.
Okay. Yeah, that's better. Thank you.
And can people hear well enough? Okay, good. There's quite a lot of sound. There's quite a lot of sound from the other room, so
Yeah, this is.
I'm the closest to it, though, I think.
Okay, I'll just talk louder or closer to the microphone. So it was really annoying to even get these packet generators to do what we wanted them. And even then, there were some optimization modules sometimes in there. Sometimes they had a kernel component that then batched them together, well, to make it faster, but that was not very helpful. And then they lied to you. And even when we managed to configure it, they still send out bursts, because it turns out it's really hard to send an individual packet to a network card. It's just not what they're designed to do. And in Munjan, this is better, but this is not a detail I'm going to bore you about. I have a 12-page paper about it, what that one reviewer described as incredibly boring to get through, but I guess it's important. So thank you for that, that excerpt. Okay, why is this even different? Well, one reason is the CBR traffic is not a good case. So typically it's not a realistic case. The internet traffic is not CBR traffic, but like people test with CBR traffic, because if you look at, for example, the old RFC 2544, it calls for CBR traffic by default and people just follow that blindly. I mean, the RFC even says you can test other traffic pattern afterwards, but the default is CBR and people are just like, oh, well, let's just do CBR and it's good enough. So this graph shows the same measurement as the result before. It's basically the baseline with plotting the latency for the CBR case, and it looks really weird. At first, it's okay, it seems to be increasing, and there's one weird spike. The spike is completely reproducible across different systems, different things, and right before it overloads, it drops completely in the latency, and the latency gets better. This is also completely reproducible. You can see there are more measurement points in there, because when I first saw this, I was like, well, this can't be true. I need to measure maybe this, so it's slightly different. But it just reliably drops there. I also have a paper about that, but it's also another deep dive into the details of how the Linux kernel and the driver works. Basically, there are two things that are trying to, well, One is trying to prevent the system from locking up from interrupt storms. That's the Linux poll mode NAPI, which just switches to some fancy poll mode and just polls the network card and disable interrupts. And then there's the interrupt throttling rate, which is typically found in all these drivers, that tries to save power. And then when it goes into power saving, that's a whole other can of worms to open. So basically, you're going to say here, power saving, kind of okay, kind of works. Also hard to measure because by default, the Linux kernel you find in most distributions doesn't report the CPU time consumed by interrupt. So it can be at 100% CPU load, but HTOP reports you are at 10% because it doesn't account the interrupt time properly unless you set the queue time accounting flag while compiling the kernel or directly read the CPU performance counters. And this is completely different paper though. So now, this kind of looks weird, and the reason why it looks weird is really that these algorithms that try to estimate the rate and so on, they don't play well with CBR traffic. They kind of get confused, and there are a few state machines, if you get them on where they keep switching between two states all the time because they get slightly confused by the CBR traffic, then I don't know exactly what happens, but you get these weird results. So let's use a Poisson process instead, and that just looks much smoother, and the result is much more what you would expect. And the only thing I'm changing between these two measurements is, again, the time between packets, in this case, from CBR to Poisson, and much more reasonable result. And if you look at real-world traffic, it's, of course, you all know that really old sitcom paper about how you shouldn't model your internet traffic with a Poisson process, but that's only really true for larger timescales. If you're running your tests of a few minutes or whatever, then you can use a Poisson process to reasonably approximate what real traffic looks like, and then you get these nice, smoother results and more realistic scenario, which is also what this is about. So what does a latency measurement often look like if you now installed Munjan and you want to drill down into really one measurement? You get these nice histograms, which are just some way to represent how the latency is distributed. And typically for many cases, you want a CDF instead, but a histogram is, well, easier to see visually. So what you can see here, these are just measurements of a few systems. The first one is a software forwarder running directly on the machine. You can clearly see there's some interrupt throttling going on. So you get this uniform distribution, kind of neat. And the second one, there's a virtual machine and a virtual switch and everything involved. Then you get this long tailish distribution, and I actually cut it off here. It's actually a really long tail, and there are some worst cases. This is also an interesting thing to measure. There are just if you look at the 99.99th percentile of some latency measurement, and then you see some horrible results there if you're benchmarking a virtual machine or anything. This can also be a big problem, and is also another thing where you can get probably a whole PhD on how this happens, why it happens, how to measure it. And a hardware box, this is just something to show how precise this really is, because if you note the x-axis, it's in microseconds and only goes up to 3.5 microseconds. Typically saying the position of the Munjan hardware timestamping approach is typically plus minus 12 nanoseconds. That is quite good for most things that typically you get latencies of a hardware box is in the range of a microsecond or maybe 500 nanoseconds to a few microseconds. A software box around 10 microseconds if it's good, and 100 if it's doing some power saving stuff. And you can see here is a nice bimodal distribution, and this is just an example where if you want to break it down to one value, your latency or anything, it doesn't really work, because what's the average of this? What's the meaning of the average of this? Is really nothing. It's the really meaning of the median of this. It's really whatever. It has two clearly distinct paths in the hardware. In this case, it was an output port that was used by multiple input ports, and there are just two cases. Either it goes through the cut-through path if there's no packet being queued from the other port, or there's a packet being queued, and so it gets queued for a short time, and then it goes to the other one. Also have a full paper about that stuff. And then I want to show you how to use it, and there's just the only boring architecture slide. Basically, Munjan sits on top of DPDK, and DPDK sits on top of the network card, and the network card offers multiple queues. And at the top, you have your users, what we call a user script. That is your user-controlled, your script, you write the whole script. And yes, there's a lot of boilerplate, and the idea is kind of you copy-paste one of the example scripts, modify it to suit your needs. Documentation might suck at some parts, but that's just your typical open source project. really, if you look at the example scripts and if you look at your basic example script that generates different UDP flows and reports the results, you should quickly get an idea of how to modify it for your needs or how to add multiple things. And the way we do multi-threading is we spawn completely independent virtual machines in the sense of a language implementation virtual machine for the just-in-time compiler. And that is really, they are really completely independent. And there are nice APIs that allow you to talk between these independent threads, but the main idea is a shared nothing approach, because in the end, what you want to generate is multiple flows, and they are often independent from each other, or you can break them down into a few independent chunks, and that makes it really, really high performance. And really have to look at the examples to get an idea of what I mean by this. So, and I will now show a quick example. I don't know how much time I've left. There's no clock. How much time I got left?
Oh, I'm sorry. You can continue for another 10 minutes.
Okay, great. This seems perfect. So, okay, I'm gonna show this example, and in this case, this example is based on our VXLAN example. This is also something we wanted to test VXLAN, and then the package generators, oh, what's VXLAN? I don't know that protocol, and well, bad luck for you. And so the first thing that you can do is you can dynamically define a complex stack of headers. And really, these are just the headers. Munjin is still a low-level packet generator, not a traffic generator, meaning there's no protocol logic behind it. We're just sending out packets, and the protocol logic is like an absolute minimum. Like we implement ARP and LACP and whatever you expect for basic functionality. And there's like the hashing algorithm to get the source port of VXLAN and so on, and to check some stuff and check some offloading. But it's not a traffic generator. Can't build a TCP stream from it. You just can build packets, but it's meant to benchmark some devices on the lowest level. And what you can do here is you can stack together arbitrary headers, and like in this case, it's VXLAN running over IPv4, and in the VXLAN, there's a VLAN tagged Ethernet frame with another IPv4 header and UDP. Oh, by the way, everything we have is also IPv6 capable, because the guy who wrote the protocol stack stuff, he really likes IPv6, and so all the examples also do IPv6. Yeah, and once you have that thing, it gets just-in-time compiled. And the next thing you do is you create a memory pool with a packet archetype, meaning this is just some basic packet. This is called memory pool. This is just maps. If you know the DPDK, then you will see how this maps to the DPDK stuff. And then you fill each of your packets with the archetype. This means you cast it to your VXLAN stack. This is initially an empty packet. You tell it, okay, I want it to be a VXLAN stack packet. And then you can call this magic fill method, which is very slow, but you only do this once. And this has nice setters basically for all the headers you have in your stack with the names that you defined before. And you can do stuff like look up a MAC address here, and you can basically set things, and then you can tell it to calculate the checksums, and this calculate checksum is again a magic method that goes through the whole stack and knows that, okay, there is this checksum, and to calculate that one. Oh, I just see the example just does it for one thing, but there's also another method that does it for all the things in your header, because I think I'm using offloading here. Okay, now this is basically the initialization. I defined my stack, I defined what I want it to look like, and then there's some boilerplate code like command line argument handling and whatever. And then the next thing is you write the actual transmit loop, meaning you write the core of your transmit loop of your packet generator test script. And this is so completely different from other packet generators, because in the end, it's not really a packet generator per se. It's a framework for writing packet generators, and you write your own one based on one of the examples and a lot of boilerplate code. So what you do here, you allocate some buffer array. In this case, it's a default batch size, and yes, this example sends out bursts unless we configure this. Well, you can't go into the details about how the write control works. Then you write the actual main loop that just checks, is the process still running, meaning did someone press Control-C, send sig term, or did another task stop it? Then we tell it, okay, nice, we want some packets from our memory pool, and we just get the packets with the packet archetype that we previously filled. We iterate over these packets and again cast them to the stack that was previously JIT compiled. This cast operation is a completely free operation. There's no cycles behind there. It's just the equivalent of a C cast, and it doesn't do anything besides tell the compiler, okay, I want to use these offsets for my packet. And then I can just access these packets at the right offsets that gets compiled down to a few assembly instructions. And I can do fancy things like, in this case, I want to randomize my destination port. I can just call master.random or whatever here, whatever arbitrarily complex processing you need for your thing. And you can, of course, access other fields here. And then you set some offloading flags and you send the queue to tell the queue to send out the buffs. And this is the whole main loop, and this is also runs typically on an independent thing, and you could start multiple threads running this. And if you look at the examples, that is really what they are doing. Now, let's say you don't want to write a script because there's this recent development that we are working on is to really provide an actual packet generator for our packet generator, meaning a set of predefined scripts that have extensive command line arguments and extensive config files, because it turns out not everyone likes writing scripts. Not everyone likes writing scripts in the Lua scripting language. I've talked to people from some companies. They were like basically, oh, but our test engineers, they are not programmers. They can just click on the Xdia GUI and click the start button. We can't use this. Okay, so let's make it somewhat easier. In this case, we did add a config file to it. This is new work, still work in progress, might be completely buggy. Well, not completely buggy, but might contain bugs. And in this config file, we just define flows. We give the flow a name. We tell that the packet type, there are a few predefined packet types. Otherwise, you can use the magic protocol stack thing again. And then this is basically the same syntax, just with a few syntactic sugar things. You need to tell it if it's a MAC address. You need to tell it if it's an IP address. And then you can define things like ranges or random ranges, which then get basically, well, not compiled to code, but they basically, it's efficient in the end. It works with a lot of anonymous functions and magic. In this case, this is your typical synflat example. Please don't copy paste and run it, because that IPv6 address is one of my test servers. And then once you have these flows, you can have a few predefined flows, or you can define your own one. Then you can run the Moongen simple interface, type in start and the name of your flow, on which device to send, on which device you want to receive, if you want to just see counters for how much stuff is getting back. And then you can set a few parameters like the packet rate, like if you want to use Poisson forward control, if you want to use whatever, how many threads you want to use by passing the same device multiple times. You can combine different flows. You can set time limits for individual flows and so on. And you get then per flow packet counters. And yeah, what you also can do here, which is often quite annoying to debug something like this, because in the end you want to know what it's actually sending out, and then you might end up using TCP dump on your destination device or our dumping method. Here is like a simple debugging interface that can show you, okay, given this config file and this configuration, the packets that I'm going to send out would look like this. Here's an example of 5 packets, and these are the fields that are being randomized or modified. And this is still work in progress, in particular now that I just recently broke the Poisson process for the traffic generation. So yeah, working on this, we'll get it fixed by next week. Somehow broke when I updated DPDK, no idea. Okay, and one last thing I want to show is how are others using Moongen, just so that you might get an idea of what have others successfully done with it and how this might be useful for you, or how this might work. A few things I want to pick out, of course, the high-profile publications. And in particular, I want to point out the DNS DDoS resilience tests, and was just recently presented at RAP 74. And they contributed some DNS logic to Moongen. It's of course not a full DNS implementation, but some boilerplate code to get DNS trails and to randomize DNS trails in an efficient and relatively simple way. They said they couldn't share the actual code for the DDoS attacks for legal reasons, which apparently something about hacker tools in France or so. But they contributed the DNS code, and it should be relatively simple to build some DNS-DDoS testing device based on top of that. So this is interesting because it uses the complex protocol stacks. And then the last thing I want to point out, this is really interesting because they actually used Moonjan how it was intended to be used. Most people just use my standard example script, which sends out randomized UDP packets and say, okay, it gets me the number of flows I type in there and it gets me a latency that's good enough. And they maybe change one line in the code. But these guys in the OPNFV project, they really built a nice test harness around Moonjan, but they actually use they support multiple different packet generators. Moonjan is one of them, was one of the first. And I really like this because they actually use the API the way it's meant to be, and they built this complex test harness, and this is a nice thing to look at if you want to automate a more complex test setup. Also, big shout out to the first paper, the Pisces P4 software switch, because they contributed the hardware timestamping code for the Intel 40 gigabit mix. That was kind of annoying work, and I haven't done it. I was just right about to get into it, and they sent me a pull request. I was like, oh, great, thank you. And yeah, so I hope you found this kind of tutorial style lesson useful. I hope maybe to find a few new users for some things. It has a broad range of applications, as you can see here, and hope you enjoyed it. And I believe there are a few minutes for questions left. And if anyone really scans a QR code ever, you can scan it here, or you can just type Moonjan into Google and you will find it on GitHub.
Hi, Dan Bogdanovic. Actually, very nice work, and I'm pleasantly surprised in packet generation. The packet generation so far has been an issue and domain of the expensive guys. And seeing an implementation using DPDK, solves many of the problems, especially up to a 10 gig space. So thank you for the work.
Thank you.
So I'll ask a question. Would it make sense to come to one of our hackathons and generate test traffic on the fly for various people doing testing of their?
That's actually a good idea.
Maybe we need you next time.
Yeah, to be honest, well, it's my second IETF, and I was not really aware what's going on at these hackathons. So
I should have thought of this, but let's get you there in London.
Oh yeah, sure.
Okay, good. Another question.
Yes, thank you. Hi, Paul. Great talk, as always. Al Morton.
You might have to get closer.
Oh, got to get closer? Like,
yeah.
How's that? You mentioned the comparisons between packet generators and the sensitivities of the devices that are being tested, like OVS and VPP and so forth. We've seen some of that in OPNFV testing. Anyway, what would you say to a specification that calibrated the generators? In other words, like policing, kind of like policing the police. I'm beginning to think, because of the sensitivities we've seen and you've seen, that might be a valuable spec to pursue. What's your thoughts?
That's an interesting idea. As I've said, I have some work on this. I believe I have a few graphs here. Like this is just 4 million packets per second and a few software packet generators, and how they, even Moonjan, when configured to use pure software, doesn't quite hit this target, which is 250 nanoseconds. But some are significantly worse. And package on DPDK, it's not visible here, but there are huge outliers in there because they print the statistics in the same thread, and it's a really bad idea. I'm just wondering how such a specification might look like. The paper we did, it's unfortunately now 1.5 years old, so it doesn't include the Cisco T-Rex packet generator, which would have been a really interesting addition. And this is what it looks like with our different packet generator, different rate control method. So what we did was we used a net FPGA for that, to just really precisely measure how the interpacket gap actually behaves, and it was quite challenging. So, any thoughts on how you would specify that?
I'm sorry, say it again.
Any thoughts on what metric you would look for, how you can break it down to a single number? I mean, what we give here is the mean squared error, but that's, I believe, not a very good metric because, yeah.
Well, I mean, if you have a target and it's as stark as comparing those two slides, Maybe just looking at the distributions says all. But I think the bottom line is we need to learn from
Roland, do you want to
really
come up?
everyone's
Sure.
work, that CBR streams aren't really realistic.
Yes.
We should have different specifications
Yes.
in the benchmarking that we're going to do. And then we need to ask the question across different generators, how accurately are they producing the streams that we desire? So we have a template and it ends up being the thing that we compare against.
Yep.
I think that's the
Because Processor is actually easier to generate because it's easier to scale up to Processor process, new Processor process. And CBR try to multi-thread that. Can't do it. Can't do it reasonably.
So I hope to see you this afternoon. Thanks.
Yes, of course.
Thank you very much. And it sounds like a very good hallway, further conversation in the hallway. We have our next speaker momentarily. We're just shifting. So thank you, Paul, and we'll see you at the next IETF. Here's your machine back. Yeah. Okay. So it should go on. Yeah. Okay. Let me introduce you. Okay, so our second speaker is, I've been practicing. No, is Roland van Rijswijk Day from IETF and SurfNet. He'll say it better, but, and he has been a speaker here before, and thank you for being here, and I think you'll enjoy this talk too.
Thank you, Alison. So it's actually pronounced Roland van Rijswijk Day, but I'm not going to torture people and force them to do that. So my talk today is going to be about the use of elliptic curve cryptography in DNSSEC, which is what the paper that got the ANRP was actually about. And I'm going to go into a little bit more detail about some follow-up work that we did after writing that paper. And also going to go into some detail about adoption of these cryptographic algorithms in DNSSEC. And since Paul did a really nice introduction of himself, I decided to add one slide about myself, because I made that step and actually wrote the thesis and defended it on June 28th this year. And this is... Thank you. This is me surrounded by my committee. You may recognize some of the people in that committee. Some of them are here in the room. So no pressure, no pressure. But I'm going to go into the meat of the presentation now. And I'm not going to repeat all of the earlier research we did. There are some pointers on the slides. The slides are actually up on the materials site for this meeting. And at the end, there is a set of references to all the papers I'm referring to. So if you want to look those up, you can look those up offline. So in earlier research, we looked at issues with DNSSEC specifically. And there were two things that we focused on, which were technical issues. The first was that if you start deploying DNSSEC, you may encounter packet fragmentation, and this can cause issues. And in earlier work, we actually saw that up to 10% of resolvers on the internet have issues receiving fragmented responses, which causes delays, or in a worst case scenario, actually causes them to be unable to resolve certain domain names that are DNSSEC signed. The other issue, of course, is that because packets are a lot larger, DNSSEC can easily be abused for denial of service attacks, and in the past few years, it has actually been abused for that purpose, and there have been reports about that in the media. Now, all of these issues are linked to the fact that DNSSEC makes your response size a lot bigger because it includes signatures and keys in the DNS packets, and in an earlier paper, we actually argued that the root cause of all of these problems might be that RSA was chosen as default cipher for DNSSEC. Because if you think about it, if you use RSA 1024-bit or 2048-bit, and every signature adds hundreds of bytes to your packet. And that quickly inflates packet sizes. So this made us wonder, can't we do anything better? Can't we use, for instance, ECC? So elliptic curve crypto, basically, for those of you who are unfamiliar with asymmetric crypto, achieves the same goals as RSA, so it's public key cryptography. You can do signatures with it. But the nice thing about ECC is that both the keys and the signatures are much smaller than they are for RSA, while they offer greater cryptographic strength. And to give you an example, a typical key size used for elliptic curve cryptography is using a 256-bit group. That gives you a 512-bit key and signature in DNSSEC, and that's 4 times smaller than, for instance, RSA 2048. So that's attractive because it makes your package much smaller. So why wouldn't we switch to ECC immediately for DNSSEC? Well, to quote RFC 6605, which is the RFC that actually standardizes the use of the elliptic curve digital signature algorithm in DNSSEC, validating RSA signatures is significantly faster than validating ECDSA signatures, about 5 times faster in some implementations. It's kind of a weird way of saying ECDSA is slower. And this potentially means that if we switch all of our signing for DNSSEC over to ECC, that we're pushing problems to the edge of the network, right? Because validators are the machines that do all this nasty work for you of doing a full DNS resolution, and they'll have to validate these signatures, and we might be increasing their load significantly if we start using these cryptographic algorithms. And actually this 5 times faster, which you should actually read as 5 times slower, is a bit optimistic. So we did some benchmarking, and it's way worse than this. So the goal of the study in this paper was, if we switch DNSSEC from using RSA to using ECC, how does that impact validating DNS resolvers, right? So rather than recommend to everyone, well, these ECC signatures are much smaller, it's really nice to switch to them, let's work out if we're not introducing a new problem by giving this recommendation. And that was the purpose of this study. So how did we go about doing this? We decided to do a measurement study and some modeling for this. And our methodology, I'm going to describe our methodology in the next couple of slides. And we started out from the premise that we had this intuition that if we knew the number of outgoing queries from a resolver, so that's not incoming queries for clients, that's the queries the resolver sends to authoritative name servers on the internet, that we might be able to predict the number of signature validations that it has to perform given that load, right? And that was our premise. And I'm going to talk you to 4 factors that influence the number of signature validations that a resolver will have to perform. Now, the first factor is that for every query that a DNS resolver sends to an authoritative name server on the internet, it will not always get a response, right? So the number of responses that come back are somehow a factor in this. The second thing is that because DNSSEC is far from universally deployed, not every response that you get back from an authoritative name server will contain signatures, right? So you won't have to validate signatures for every response that you get back. The third factor is the number of signatures in a response that contains signatures, right? Because while you might expect a response to contain a single signature for the record that you requested, actually we observed that on average, every response that contains signatures has somewhere in the order of between 2.4 and 2.5 signatures per response that has signatures. That's because there are signatures in the additional section. There might be extra records in there that require signatures. So this intuition doesn't hold. There are more signatures in a response than just for the record that you requested. Finally, your resolver may not have to validate each and every signature in that response, either because it's already validated one and it's cached it, or because it's in the authority or additional section and it decides not to validate those, right? It doesn't have to validate those. And another reason for why it might not validate signatures is because it doesn't have a full chain of trust all the way up to the root, so it might not be able to validate that particular signature, and it's not going to bother to spend the CPU cycles on it. Right. And to remind you again, we do not measure the number of queries from clients because that varies strongly between resolvers. We wanted to build a model that we can apply to any resolver regardless of its client population. And if I'm not going to go into detail in the presentation, but in the paper you will see that the model is actually a little bit less accurate for resolvers that have a small client population, but those are the resolvers that we really don't have to worry about as much because they will be validating far fewer signatures because they're processing far fewer queries. Right, so how did we measure this? This picture shows you our measurement setup. And on the left-hand side, you see clients, which is typically you with your laptop, unless you're an idiot like me that runs a resolver on their laptop. And then what we did was we captured traffic that was going to production DNS resolvers, and then we forward this traffic to an instrumented DNS resolver. So we're sending a copy of the exact query traffic that goes to a production resolver to one that we instrument, and then we measure certain factors on that. So to make sure that our instrumented resolver is actually performing in a normal way, we measure the number of queries from clients and the number of responses sent back to clients, which you see on the left-hand side marked as QC and RC, and compare that to the production resolver, right? Just to make sure that we're observing the same thing, right? Because if we instrument the resolver and we break it and it doesn't respond to clients as it should, that would be a mess, right? And there's some stuff in the paper about the ethics of this, because of course we're sending people's traffic to an instrumented resolver, and we don't want to violate their privacy, so we took some measures for that. On the instrumented resolver, we measure on the outgoing link towards the internet, so where the resolver talks to authoritative name servers, the number of queries it sends, so all of these factors that I talked about in the previous set of slides, and the numbers of signatures that it validates, and for that we actually had to alter the code of the resolver, right? Because this is not something that most resolver implementations typically keep statistics for. So in this case, we modified bind and unbound to record this number of validated signatures. If we then look at all of these 4 factors that I described in the methodology slide, and you plot those as a scatter plot, then you see from top left to bottom right all of the 4 factors. So A shows you the number of queries on the x-axis, number of responses that come back on the y-axis. B shows you the number of responses on X versus number of responses containing signatures on Y. C shows you number of signatures per response, and D is number of signatures that are actually validated, or fraction of signatures that's actually getting validated. Now, if you look at these graphs, then your intuition might be that you could model this with a linear model, although especially graph B has a lot of noise in it. But as it turns out, graph B is not the one that we want to worry about, which is the number of responses that contain signatures, because we're actually going to use that later on in the model. So there, the accuracy is not an issue. For the other ones, we tried if we can approximate this with a linear model, and it turned out that we can. So I'm not going to talk you through all of this, but the details are in the paper. But we created a simple set of linear equations that you can then combine to make a model for a validating resolver. And it has 4 important parameters. So the first one is the average number of responses per query. And this is something that you need to measure on an operating resolver to actually populate the model. So these are parameters that you would need to measure. The fraction of responses with signatures, the average number of signatures per response, and the fraction of signatures that is validated. Oh, is the mic broken again?
Oh dear.
Better? Oh. Okay, I'll try to eat the mic, as somebody suggested yesterday. Okay, so of course, if you make such a model, you need to validate if it works. So we set out 4 criteria that we use to validate this model. Now, the first one is that we wanted to make sure that the model works for different DNS resolver implementations. So we tested it for unbound and bind. And actually, I had a student do some tests with PowerDNS as well, which at the time they were implementing validation in their resolver. Unfortunately, it wasn't stable enough, and the same is true for not resolver, which was then still under development. But in principle, you could apply to those 2, and we did some tests with it. Now, the second thing we wanted to validate is whether the model has stable properties over time. And actually, like I said, only alpha S, which is the number, the fraction of responses that contain signatures, can vary significantly over time, because we vary this parameter to make predictions, right? So we don't really care if that's stable over time. But the other factors should be more or less stable over time. So we measured over a 5-month period and didn't see major changes in these 2 in the rest of the parameters of the model. We also wanted to make sure that this model works for different client populations, so we used traffic from 4 sources to test the model. So I work for SurfNet, the National Research and Education Network in the Netherlands. So we used traffic to 3 of our production resolvers, but we also used traffic to one of the resolvers for my university. And in addition to this, because we realized that we may not have typical resolvers because we have certain client populations. We also did some worst case estimations that are in the paper, where we take sort of worst case estimates for all of the parameters of the model. And finally, we checked if the model is actually a good predictor of empirically observed data. So what we did was we populated the model, made predictions of what we thought the number of signatures that we need to validate was going to be, and then compared that to what we saw in actual practice. And again, the details for that are in the paper, but we did some statistical goodness of fit tests for that. Now, the next thing that we have to do is, now that we have a model for predicting the number of signature validations that are required, we of course need to know how ECC performs, right? And although there are some benchmarks publicly available that we used in an earlier paper, we wanted to make sure that we had up-to-date benchmarks. So we took 5 implementations of elliptic curve cryptography and benchmarked those on a modern CPU. We took 3 versions of OpenSSL, one that we consider legacy, so you'll see that in older distributions, one that we considered long-term support because it's in all of the long-term support versions of, for instance, the major Linux distributions, and one that we considered at the time to be new and optimized, and it's actually moving into long-term support now. And that had optimized implementations of ECDSA P256. So that is the algorithm that we expect will be used the most in DNSSEC at this point in time. And actually, there's now OpenSSL 1.1.0, which does not perform that differently from 1.0.2. So this is actually still a good set of benchmarks to use today. Then we looked at the newer elliptic curve algorithms, ED25519 and ED448, which have only recently been standardized for use in DNSSEC. And there again, we took optimized implementations of these two algorithms because the reference implementation of those don't perform very well. So we took optimized versions there. And then what we did was we did 100 tests of running the algorithm for 10 seconds and then measuring how many signature validations it will perform in that period. And the details of the benchmarks are in the paper. To give you some idea, so ECDSA P256 is an order of magnitude slower than RSA 1024. And why is that a good comparison? Because you could argue that we're comparing apples and oranges, right? Because ECDSA P256 cryptographically is much stronger than RSA 1024. But I would argue that you need to make this comparison because most of the signatures that you see in DNSSEC today are signatures with zone signing keys that are 1024 bits. Whether that makes sense in terms of security or not, you can debate, but that's the case. And then if you take ECDSA P384, which is cryptographically even stronger, and you compare that to something like RSA 2048, you will see again that there's an order of magnitude performance difference. So this is way more than the 5 times that is quoted in the RFC. Even ED25519, which is way faster than the ECDSA algorithms in terms of implementation, that is still almost up to an order of magnitude slower than RSA 1024. And only for, if you compare it to RSA 2048, do we get into the same sort of order of magnitude as is quoted in the RFC. Right, so some key benchmarks, because you're going to see these in the graphs that I'll be showing you a little bit further along in the presentation. You see 5 implementations on the left-hand side, the specific elliptic curves that we did the test for, and then the performance in the number in terms of the number of signature validations that you can perform with that algorithm per second on the CPU cited at the bottom. Right, this is not a top-end CPU, but it would be a common CPU that you would encounter in server architecture. So this is typically something that people have in their data center, right? We have data centers full of this stuff. Unless you're really rich in your Google, you have these. And why did we pick these particular benchmarks? Because you're going to see them in the graphs that I'll be showing you in the next couple of slides. So we picked ECDSA P384 because this was a worst case scenario, right? This is the slowest of all of the algorithms that we benchmarked, and it is the strongest broadly supported cipher. And what do I mean by that? You could say that ED448 at the bottom of the slide is stronger in terms of cryptography, but it's not widely available in implementation, so few people are going to use it. So that's why we took P384 as sort of a benchmark to compare against. Then P256 on OpenSSL 101, we took that for as long-term support version of the most likely used cipher. The 102 implementation of P256, as you can see, that is almost 3 times as fast because of the optimizations in there. And this is to show you what an optimized version of ECC can do. And then finally, newer algorithms which outperform the older ones by, well, ED25519 is again another 1.5 times faster than the most optimized version of P256. Although I've actually seen a paper recently that claims that they can make P256 almost as fast as ED25519. Right. So let's go back to our original question, which was, what is the impact on validating DNS resolvers, right? Because that's why we started this. So we use our model to evaluate or to estimate future performance, right? And we look at 2 scenarios. So the first scenario is, what if we take current DNSSEC deployment and we switch all of those domains over to ECC overnight? So everything that's now signed with RSA or DSA or whatever you use, we all switch that to ECC. Is that an issue? Well, based on the measurements that we did on our resolvers, we argued that you need about 150 signature validations per second for a busy resolver. This was a resolver processing around 20,000 queries from clients per second. So this was a busy resolver, and that's not a problem. And even if we take the model and we put in the worst case numbers, we still don't go above the worst case scenario, which is using P384. So that's not an issue. But what if everybody deployed DNSSEC and if they used ECC, right? So right now, DNSSEC deployment is roughly 3.5% of all domains on the internet. What if 100% of those were to deploy DNSSEC and they all use ECC to sign? What does that do to your resolver? So the second scenario that we evaluated is a popular domains first growth to 100% DNSSEC deployment. And everyone uses ECC. Now, what do I mean by popular? By popular, I mean that the domains for which the resolver sends the most queries to the internet, if that switches to ECC first. Right? And so here I plot the query popularity for queries that the resolver sends to authoritative name servers. And this shows you this is a classic, so you can see the axes are log-log, and this is a classic internet distribution. It's commonly referred to as zip for long-tailed or Pareto or 80-20. Doesn't really matter, but basically what it means is that the most popular query is by far responsible for the highest number of queries sent out to the internet. So let's look at some results. So these are the really nice graphs that my student cooked up. He's a MATLAB wizard. And what you can see in this graph on this axis, and we can debate what you call that axis, but I would say it's the y-axis. You see DNSSEC deployment, and as you may remember, I said that we would be varying the average number of responses with signatures to simulate DNSSEC deployment. Right, so what we did was calculate, based on the distribution for popularity, we modeled what if we go from left to right in that distribution, how many queries with, how many responses with signatures would that result in, and that's what we model on that axis. So from 0 to 100% DNSSEC deployment. On the x-axis, you see the number of outgoing queries, and actually the maximum number of outgoing queries we observed on the busiest resolver was some 1,800 queries per second. And then you see a gray plane in the graph, which is the maximum number of signatures that we can validate for ECDSA P384 on a single CPU core. The takeaway from this is that there is ample room for growth in DNSSEC deployment and outgoing query load, right? So we can go up to 100% DNSSEC deployment using ECDSA P384, and the number of outgoing queries from that resolver could still double, and Unbound would still be able to validate those signatures on a single CPU core, right? And so this is a conservative estimate. If you run a really busy resolver and you're working at an ISP, you typically don't have a single core assigned to that resolver. So this is something that is easily within the realm of the possible. So that's a great result. We can take the worst case algorithm, and Unbound will still be able to cope with it. So what does this picture look like for Bind? I apologize because the title of the slide is somehow gone, but this is Bind. And for Bind, we observe something a little bit different. There might be a potential problem for P384, because as it turns out, Bind validates up to 2.5 times the number of signatures for the same query load that Unbound does. Where's that?
Interesting.
Okay, sorry. There have been suggestions for reasons why that might be, because Bind might be trying to chase, if it gets negative responses, it might be trying to chase up other authoritative name servers. It really tries very hard to get the response, and it might be validating more signatures because of that. But we actually didn't investigate in detail why this was the case. We just took this as a given. But what you can then see is, if we look at the situation for the ECDSA P256 long-term support version, which is actually the one that we expect people to use if they sign, then you see that even there, Bind has ample room for growth. So the green line that intersects the red slope intersects it way beyond the number of queries that we would need to be able to validate signatures for on our busiest resolver today. And the same is true if, for instance, you want to go for something really strong and you don't even go for P384, but you go for the newer curve, ED448, that outperforms even the long-term support version of P256. So the takeaway from this is, in most cases, Bind will cope, but there are slight worries for P384. Now, after the original paper, we did some additional benchmarks, because you could argue that we did our benchmark on Intel x86. Some of the optimizations that have been implemented are only available for x86 architectures. So what about other architectures? What if I have a home router and I want to do DNSSEC validation on that? How is it going to cope? So we did a student project, and actually had two students working on this, where we did benchmarks on ARM CPUs and on MIPS CPUs, because we think that these are representative of what you would find in a typical home router. Now, the key, I'm not going to go through all the details of those benchmarks, but the key takeaways there is that the performance is low, but it is more than sufficient for home scenarios. Interestingly, ECDSA may sometimes be faster than EDDSA, because there are already some optimized versions of ECDSA available for instance, ARM CPUs that outperform the stock EDDSA implementations that are available for that. We did an n=1 home router experiment. So this is take with heap of salt, right? This is not representative, but it's an interesting experiment to run. And one of my students really wanted to do this. And I mean, he got extra bonus points for the fact that he got informed consent from his roommate before he did the experiment, right? So, and I didn't even have to encourage that, because it turned out he had an ethics course going on at the same time. So, and there are two takeaways. So this shows you 24 hours of queries to the resolver that they run in their student dorm, which he equipped with Unbound and then instrumented and then measured. And there are two takeaways from this. And the first one is a little bit serious, in the sense that with 10 concurrent users, so he did this during a party. So there were lots of people in the house, and with 10 concurrent users, the query load peaked at around 60 queries per second from clients, right? Now, he also measured cache performance on his resolver, and the cache performance was atrocious, right? Because there are too few users to make good use of the cache. So actually only about 10–20% of his queries could receive responses from the cache. So I said, well, let's go for the worst case. the cache doesn't do anything, and the resolver has to validate everything. And then you see that if you would run this on a MIPS CPU, and we take some of the benchmarks that they perform, that the resolver would actually start to struggle, because these home devices typically have only a single CPU core, and that CPU core would be swamped with signature validations at peak load. So there's maybe some work there, but this is actually only if we have 100% DNSSEC deployment, which today we don't have. So I believe we can safely assume that by the time, if ever we reach 100% DNSSEC deployment, these devices will be fast enough, and there will be optimized implementations of the elliptic curve algorithms. Oh, and the second takeaway from this is that student parties are not what they used to be. Because the observant viewer will see that the party stopped at 1 a.m. Oh, there's a question.
Is this a representative student party where people are browsing the web instead of getting drunk?
Yes, these are millennials, so they're checking Facebook the whole time, posting selfies. I mean, yeah. Actually, my student was really. I told him not to look at the queries, and of course he did. And then he thought, I don't want to know this about my roommates, and he gave up on it. So I want to end with some insight into adoption, right? Because I've written a couple of papers on use of ECC in DNSSEC, but until 2015, there was virtually no adoption of ECDSA signing schemes that are standardized in RFC 6605, and RFC 6605 dates back to 2012. So, and actually the first implementation in bind and unbound is a little bit older than that, right? Because Wouter Wijngaards, one of the authors of the RFC, is also one of the developers that implements unbound. So there was support in unbound actually before the RFC came out. So in late 2015, Cloudflare actually was the first DNS operator to adopt ECDSA signing at scale, right? They rolled out their DNSSEC as a service thing, and they said, Oliver Gudmundsson said, we're going to be signing with ECDSA. So we want to know, how has adoption developed since then? These graphs are for .com.net and .org, and what they show you is the period from the 1st of March 2015 until somewhere last week, before I got on a plane. And what you can see, I guess the legend is a little bit hard to read, but I'm going to be pointing out some things, such as the fact that the majority of signed domains in .comnet and .org still use RSA SHA-1. That should change. SHA-1 is not considered secure anymore for signature algorithms. This is the point in time where Cloudflare announces its universal DNSSEC using ECDSA P256. And as I hope you can see, there is an uptake of ECDSA that starts from that point onward, right? The pink area at the top of the graph starts growing slowly. But actually, ECDSA adoption is now driven completely by other operators that are adopting this en masse. As of, I think, the beginning of this month, ECDSA is the second signing algorithm after RSA SHA-1. Please, people, change that. Replacing RSA SHA-256 as second popular signing algorithm. So that's actually good news. This is getting adopted pretty quickly in .comnet and .org. If we look at then the two TLDs that have the largest number of signed domains, which is .nl and .sc, the picture is a little bit different. As you can see, that adoption of ECDSA P256 is still quite low. It's only a fraction of the total number of signed domains. But one takeaway here is that especially .sc is doing really well, right? No RSA SHA-1, it's all RSA SHA-256, so kudos. That actually makes way more sense. And they're actually going to switch the signature algorithm for their TLD to RSA SHA-256 as well at the end of this month. In .nl also far less RSA SHA-1 than in .comnet and .org, but also only a little bit of ECDSA. So the takeaway is the early large-scale adopters of DNSSEC take longer to get a significant share of ECC signed domains. It's not surprising, but it also means that replacing signature algorithms will take time, also because replacing signature algorithms is actually difficult. If we look at the Alexa top 1 million, completely different graph, also quite interesting. Here you can see again that there's quite a bit of adoption of ECDSA P256. 22% of the Alexa Top 1 Million signed domains, and about 1.7% of them are signed, use ECDSA, and 61% of those use Cloudflare. So there's actually also quite a significant number that are not using Cloudflare for this, they're using another operator. That's interesting. Right, so I get to my conclusions. The first main takeaway from the paper and from this talk is that ECC is sufficiently performant for use in DNSSEC, right? We can easily validate the number of signatures that we would need to validate if everybody deployed DNSSEC with ECC on a single CPU core and still have room to spare. So my recommendation is going to be that operators should switch to ECDSA for signing. If you haven't deployed DNSSEC yet, don't bother deploying RSA. Please go for ECC algorithms straight away. Because it gives you all of the benefits of ECC, which is smaller DNS packets, which means no fragmentation. We showed that in an earlier paper, fragmentation is fully gone, and much less amplification. And if you combine that with some of the newer ways to tackle amplification attacks, then the combination of switching to ECC and deploying those countermeasures will actually make your domain unattractive to abuse in amplification attacks. Finally, resolver operators may want to look at deploying newer optimized crypto libraries to have some CPU to spare. You can do this even with long-term support versions of the software, but if you want to save on CPU cycles, you might want to deploy newer libraries. And finally, as I showed you in the last couple of slides, adoption is slowly taking off. And with that, I get to the end. I would like to thank my students who helped me with this. So that's Kasper Hageman, who just started his PhD at Aalborg in Denmark, Bruce and JJ, who helped with the ARM and MIPS benchmarks. The data for the adoption was supplied by the Open Intel project. Have a look at the URL if you're interested. And the references to the papers, as I said, are included in the PDF of the full slide deck. Thank you for your time. So, any questions?
I'm Sriram from NIST. So we have been working on BGP-SEC implementations, which also uses ECDSA P256. And NIST, together with SBIR contractor, the company's name is Antara Technic. So together we have developed a high-performance implementation of BGP-SEC, and in that we did. I mean, it was mainly our SBIR contractor Antara Technic, and his name is Mehmet Edalier. So excellent work. You should look at that. We presented that paper at NANOG 69 in February this year. It will say BGP-SEC, high-performance BGP-SEC implementation, but it has a lot of measurement details about ECDSA performance. And we compared it with OpenSSL 1.1.0 and significant, I mean, significant multiplication factor improvement of this high-performance implementation compared to OpenSSL 1.1.0. So I'll be happy to give you the pointer to that paper.
Okay, thanks. Well, that was actually the paper I was referring to when I said that there might be an even faster implementation of P256. But and it's great work. Thank you. Thank you for that. And thanks to NIST for sponsoring that.
Wes Herdeker, SI. Thanks. This is really good measurement work, and I enjoyed seeing the results quite a bit. You know, this sad thing, so two things. First off, the sad thing is that, you know, you are providing guidance to signers, but it's really the resolvers don't have a choice, right? So if there was like a sudden uptake of DNSSEC usage, and, you know, that could eventually blow through the roof, and if everybody used elliptic curve, you could still imagine that, you know, although you state at the end that everything's okay right now based on the current growth of DNSSEC, you can imagine the case where it actually might be a problem down in the future, you know, based on the fact that they're still significantly slower. And that actually brings me to my next point, which is it would actually be interesting to look at, you know, what DNSSEC adoption rate might combined with, the CPU increase in speed and have this early warning system of we're headed for danger because all of a sudden the resolvers are not going to get it, if all of a sudden some major, GoDaddy or something, started signing everything. I don't know.
I would highly encourage GoDaddy to do that, and stop charging people money for using DNSSEC. So there's actually some discussion about that in the paper. And in the paper, we argue that even if you go for worst case scenario, so where we take away all of the measurements and we just model, we assume that the model is accurate enough to put in worst case parameters. It's arguable whether everybody has the CPUs that can deal with this, right? But that's an assumption, and that's an assumption that we cannot not prove or disprove. But even if you put in worst case data, then with the way the DNS currently looks, I am confident enough to say that resolvers would be able to handle the signature validations. However, if suddenly the new GTLDs become wildly popular and we see a fragmentation in the namespace, then this picture might change, because that might blow up the number of cache misses, which might blow up the number of signature validations, and then we are in unknown territory. But it doesn't seem like the new GTLDs are that wildly popular, so I'm not too worried about that yet. But there are, and these are actually discussed in the paper, so there are some situations where our assertion that we can deal with these signature validations where they might not hold, and this is one of those situations. The other one, which is also discussed in the paper, is about, what did it do? No. Oh, can I just reopen that? Oh yeah, okay, there we go. One of the other things that we discussed in the paper is a denial of service attack, where you try to cause CPU starvation by forcing signature validations. And this is actually something that Paul Abersman, who was then still at Comcast, brought up. And we actually verified this, so and that's also in the paper. What we did was we forced resolvers to do lots of ECDSA signature validations by making them verify signatures for Cloudflare's sort of black lice thing that gives you a fresh signature for every NX domain. That can kill bind easily. Unbound survives. So there is an issue there, but we also sketch an idea of how you could solve this in resolver implementations by doing some form of rate limiting. And I know I've discussed this with Wouter from Nelnet Labs, who thought it might be feasible to do that. I don't know whether he has had time to implement it yet. Does that answer your question? Okay.
Dear defendant, congratulations with your work, but I still want to reflect on some of your results. Well, you made some analysis of the. You made some analysis of the number of signatures validations done by Unbound and Bind. Can you also continue this kind of work or reflect on this work and say something about what is the ideal? If I could build a platonic or an ideal resolver, what are the number of signatures I have to validate to come up with an answer?
Okay.
It's not the measurements actually, but it's more the theoretical approach, and that can give maybe some guidance to the software developers.
Yeah. Learned opponent. Thank you for your kind words and interesting question. But seriously, this idea of designing a platonic resolver, I like that. I really like the term, so I'm going to have to steal that from you and use it somewhere. That's actually interesting because as the paper states, there's a huge difference between bind and unbound, but there are many factors that play a role in that, right? A platonic resolver, you would need to specify requirements, what that does. Does that give you, does that work the hardest to get you an answer? Does that find some middle ground between spending time finding something and then deciding it can't be found? those are questions that would need to be answered, but I think that's interesting research. So we have a PhD student in our lab who's working on resolver things, and this is yet another idea to put in his head.
Thanks. Indeed, we can make explicit decisions.
Yeah. No, and I think that this is...
we know the
yeah.
theoretical costs of these decisions.
I agree. So there's actually, in my opinion, far too little research on what is the optimal resolver. And for instance, we can talk about caching strategies, we can talk about time spent finding responses. So I think that, yes, I agree with you. There is interesting research to be done there. Thank you.
Thank you very much.
Willem Torop, NLNet Labs. So very nice work, very interesting, definitely quality work, and it's very important to find the right measurement metrics. So I think it's very nice that you identified those factors. But however, there are some factors which are underexposed in now current scientific work. And, you know, there's this single factor which is of paramount importance. And I think you know what I'm talking about. And, you know, it has driven many scientists to madness. And it's a difficult beast to capture. I recognize that. And so I don't expect that you did an attempt, but have you looked into the Gallimaufry factor?
So that's a really good question. And yes, it did nearly drive me insane, but I have a backup slide on that. So we actually measured the as you can see in the graph here, we measured the Gallimaufry factor. I'll talk you through what you see in the graph here. So what we did was we measured the Gallimaufry factor in micromorphies for queries per second leading to ECC validation. Well, I think that Willem already said this. Everybody knows this factor.
Micromorphy can be, you know, the mingle, miscellaneous, or yeah.
And so you see the initial ramp down, right? Which is what you would expect to see typically in a Gallimaufry distribution. And then some normal noise, but then there is this weird peak, an unexpected rise around 425 queries per second, which we can't explain. Right, so and that has puzzled us for the past year and a half. And if you know what causes that, I would like to know, right? So, and we see this for unbound and for bind, and there's also this suspicious absence of noise beyond 450 queries per second. So, help us.
So there are quantum factors actually that influence the micromorphies a second. So it's actually a different measurement unit every time, right? So it could be electrical radiation from satellite debris, or the static from nylon underwear. But I suspect that this will be the micro mischief assignments. the peak you'll see there.
Okay.
So, but anyway, I'm very impressed that you managed to capture this. So it's definitely it surprised me that someone would win twice the network research applied network research prize. But now I understand why it is, because you know.
Thank you, Alison. Do you have any questions about this?
I'm concerned that the audience is wondering if they've gone out of their minds, if they have not heard about this. So we should explain that Willem has been challenged, and now he's taken Roland into a challenge to use the word Gallimaufry at 3 mic lines. And this was a very successful version of that, as well as a deep enlightenment of an important scientific factor.
It's good,
and micro factor.
And I think our ploy to surprise you worked. Yes. So let's go back to the serious questions in this case. Unless Matt wants to ask me a question about the Gallimaufry factor.
Matt Ford, not with NLNet Labs. Can you go back to your ECC adoption slide?
Yep. Which one?
Keep going.
That one?
No. Yeah, maybe it was the one you said. Yeah, one after. So anyway, that'll do.
Sorry.
Yeah, I'm trying to understand this because it looks like there was a lot of growth around this time last year, and then it's actually been pretty flat in terms of ECC adoption since then. Do you have any reflections on that?
Yes, I do.
Observation?
So what, let me see if the pointer on this works. What you're referring to is here, where there is, especially in .org, it's very steep. This is, we actually looked at that in detail, what happened there. And this is one operator in particular who was using RSA SHA-256 before, and they decided on their own to switch to ECDSA P256 for all the right reasons, because they wanted to reduce their packet sizes, they wanted to increase the security of their signature algorithms. I think I'm trying to struggle to remember the name. Oh, it's Domain Name Shop. It's a Norwegian company, and I can mention their name because I had some email communication with them. And they did this. It's actually not been flat. It's kind of hard to see in the graphs here. If you look at the slides, you can zoom in a little. So there is still some adoption, and it's still increasing slowly. But the large peak was when this one organization decided to switch. And then later on, there's a smaller bump that you see if you zoom a little bit into in on the graphs. There's another small bump, which is another algorithm rollover. And actually, I applaud these people because I monitored their algorithm rollover. They did it completely correctly, right? So those of you familiar with DNSSEC will know that this is difficult. To give a little bit of idea to the people that are less familiar, an algorithm rollover requires you to take very specific steps, which is to introduce new signatures first before you introduce a new key. Because DNSSEC actually has this provision that if something is signed with a certain algorithm, so if a key for a certain algorithm exists, signatures for that algorithm must also exist, because otherwise you'd be able to perform downgrade attacks. And most resolver implementations take that quite strictly. So if you don't follow those steps in an algorithm rollover, your domain goes bogus, and resolvers will actually refuse to validate it. So they did this correctly, and I think that was the first example at scale of switching to a different algorithm that was done successfully. Because we've seen algorithm rollovers for TLDs and CCTLDs in the past, and almost all of them have had some hitch where they, for instance, introduced the key at the wrong time, or made another mistake, introduced the DS at the wrong time. So this really is something that needs attention. And to finish off with that, as I said, the Swedish registry is going to switch from using RSA SHA-1 to RSA SHA-256 for .SC, and we'll actually be measuring that. I started this other project called Root Canary, which we presented at the MapRG meeting earlier this week. The Swedes actually came to us and said, can you measure our algorithm rollover? Because we're kind of scared that something might go wrong. So we're actually going to measure that and see how that works in practice. So we get a much more detailed measurement than we have for this particular instance, where we only have a granularity of 1 day intervals.
Well, thank you very much. This is great work. And congratulations on winning this prize for the second time. I should say that Roland's now been invited to join the selection committee for the ANRP, so no good deed goes unpunished.
Thank you.
Yes.
Any other questions? Okay, thank you for your time.
Thanks, everybody. I think we should end on this high note. And so, please feel free to cluster up here and ask any questions or get involved further. I wanted to show you the cat who was working. So let me quickly do that. And then we'll end on that note. But does anyone else have any questions of a general nature before we go? Gee, when you're trying to do things, you can't. All right. Okay, so go out and write papers the way this cat Al does, and and send them here and participate in IRTF. Thank you. So we'll give everybody back some time. I think we have to do a presentation of certificates, which we don't have to do in front of everybody. Olaf, do we have certificates to present? Sorry. Yes, so we are going to actually, if you want to stay and work in here, you can see the presentation of the prize certificates and the photographing of same. Thanks very much for being with us. We were really very good session. Yes, please. Thank you.
I might be able to head and show the privacy.
Good, good. Well, talk a little bit about what your vision for the and how we can set up a okay, yeah.
Is there other people working on it?
Well, I'd want to have it's one of my health course, but I'd want to have also a review board in it as well, so to see so there's some people who are definitely interested in that and having someone who has resources to be a chair.
Yeah, I mean, I think one of the initial things that needs to be done is I don't think at this time entire piece has a political concept of what elements of privacy are easy. It's the obvious one to just hold up the world harder aspects of privacy.
And bringing, there's a tremendous amount of research that's been done. It's been very little.
Okay.
Yeah, so in fact, exactly the kind of thing we were talking about yesterday about having no idea what we're supposed to have.
Right.
We really need to be able to